हरि करना।
So as I have told you, to calculate the t distribution, you need to know the degrees of freedom df and the value of the t statistic. So the degrees of freedom represent the number of independent observations in the sample and are calculated as the sample size minus 1. That is, degrees of freedom is equal to n minus 1, where n is the sample size. But does it make any sense when I say degrees of freedom is equals to n minus 1? Can you make up anything out of it? Can you make out anything out of it? I'm not sure whether you're able to make out anything out of it. So that's the reason. Let me explain what does degrees of freedom mean for us. So let me put degrees of freedom, that's is equals to n minus 1. So df is equals to n minus 1. So the term degrees of freedom in statistics refers to the number of variables or number of values in a sample that are free to vary when estimating in statistical parameter. So I'm repeating again what exact meaning of degrees of freedom in, you know what's the meaning of degrees of freedom in mechanics? Okay, degrees of freedom, how many degrees of freedom a link or an element has will tells how many, in how many axes it can move. Simple, very simple. The same thing applies here also, but here in spite of the element you take the values in the data set. That's it, I'm making pretty simple. So the term degrees of freedom, that's DOF or DF in statistics, refers to the number of values in a sample. Of course, sample is a data set. In a sample data set that are free to vary when estimating a statistical parameter. You know what's parameter? I hope you know that. The parameter is the measure of population. So in this case, T distribution, so the degrees of freedom is calculated as the sample size minus 1. So the idea behind the term degrees of freedom is that when estimating a parameter from a sample, there is some loss of information due to the fact that the parameter is being estimated from the sample and not from the entire population. So this loss of information is reflected in the reduction in the number of degrees of freedom. So when calculating the sample mean, for example, we use the sum of the values in the sample, but when we have to subtract one value from that sum to estimate the population mean, this is because once we know the sum of the values and the sample mean, we can determine the value of the last observation since the sum of all observations is fixed. This means that there is only n minus 1 observations that are free to vary. That is why we subtract 1 to get the degrees of freedom. I hope you're getting what I'm trying to explain with this much of pain. So what I'm trying to tell is, when you calculate mean of the sample, let's take the mean of the sample because that's what at the end of the day you're using to estimate the parameter of the population. So mean of the sample is equal to sum of all the values in that sample divided by sample size. Am I right or not? Of course I am. Sample size. Okay. So now when I want to estimate the population parameter, I'm gonna use a t statistic or g statistic, whatever it may be. I'm gonna calculate. I will do this kind of formula. X is the value from the same sample minus mean of the sample whole divided by, you know what it is. Let's take, if it is z value, just let's take whatever t or z and divided by, that's it. Okay, so when you are doing this, so what you're doing, at the end of the day, when you're doing this, so in this case I'm going to put the standard error here. It's SE, so standard error. So when, let me change this to, yep. So at the end of the day, what we are doing is, you have a variability. You have a variability to use only n minus 1, because one is fixed. One is, you have to use this. You have to use this to estimate. Always you have to use one value from the sample to estimate the parameter. So that one is fixed. Other than that, how many variables that are available for you? How many values from that sample are free to vary to estimate statistical parameter? Obviously n minus 1. Correct? So that's what I'm trying to say. That's what the degrees of freedom is. So degrees of freedom is number of values in a sample that are free to vary when estimating a statistical parameter. You will have only n minus 1 values are free to vary, because one value always, whenever you calculate a test statistic, one value has to be taken, then only you can do that. So that value you have to exclude. If you exclude one, how many values that are free to vary? N minus 1 only. That's what is called degrees of freedom. Let me get back to my work. Okay, I think the concept of degrees of freedom is clear for you. So the concept of degrees of freedom is important in statistical inference because it affects the variability of the estimated parameter. When the degrees of freedom are smaller, the estimated parameter is more variable, and this affects the precision of statistical tests and confidence intervals. Let's do small animation. Let's do the small simulation. Sorry. Okay. So this is a student's t distribution simulation. This is our variation, that's degree of freedom, DOF. Okay, and here you can see mu, that's population parameter which is undefined, and here you see the sigma, standard deviation, and x undefined, and here you can see the variance. These are all undefined. Let's take a degree of freedom. So what we are trying to say, when the degree of freedom are smaller, the estimated parameter is more variable, and this affects the precision, statistical tests, and confidence interval. So this is what happens when this one is smaller. When this is increasing, your distribution is also increasing. Let me put it to 10. So it's becoming better. And let me bring it up to 50. So it's becoming more better. if I increase that, it's becoming more better. And you can even see the standard deviation. Of course, mu we can, and variance and standard deviation you can see. And let me bring it to 1. It's not defined. Let me bring it to 10. It's 1.118 and 1.25. It's not that great, but when I make it to 100, when I have more number of values which can vary, then I have better results. So when the degrees of freedom are smaller, the estimated parameter is more variable, and this affects the precision of statistical tests and confidence intervals. Obviously, that's what happens. Okay, so now in summary, the term degrees of freedom in statistics refers to the number of values in a sample that are free to vary when estimating in a statistical parameter. In this case, t distribution, the degrees of freedom is calculated as the sample size minus 1, where n is the sample size. The idea behind the term degrees of freedom is that there is some loss of information when estimating a parameter from a sample, and this loss is reflected in the reduction in the number of degrees of freedom. So the concept of degrees of freedom is important in statistical inference because it affects the precision of statistical tests and confidence interval. So now it's closer. See what at the end of the day, degrees of freedom is nothing but n minus 1, correct? Correct? It's n minus 1. So degrees of freedom is just an n minus 1. Now n minus 1 is nothing but the sample size minus 1. What central limit theorem says? If the sample size that you take from the population keeps on increasing, it will get closer to the normal curve. Correct? Let me show that. What is this? Something random. Getting better. I'm increasing the sample size, of course, the df, but df is sample size minus 1. Better, much better. Okay, so that's what is degrees of freedom for us. So now let's get back to our work. Now let's calculate the t statistic, because I hope you're damn clear about degrees of freedom. So now let's move on to the t statistic. To calculate the t statistic, you first need to calculate the sample mean x bar and the sample standard deviation s. Then we can use this formula. T is equals to some sample mean minus mu, which is hypothesized population mean. Mu is the hypothesized population mean, and x bar is the sample mean, and s is the sample standard deviation, and n is the sample size. We will call it a standard error. So once you have calculated the statistic, you can use a t distribution table or software to find the p-value associated with the respective t-value and degrees of freedom. So the p-value represents the probability of observing t-value as extreme or more extreme than one calculated assuming the null hypothesis is true. So for example, if you have a sample size of 10, so sample size of 10, I got a sample size of 10 and want to test if the sample mean is significantly different from the population mean of 5, and you calculated t statistic of 2.31. I got the t statistic of 2.31. So my t static value after using the formula, I got 2.31. Okay, and on the other side, the degrees of freedom, because my sample size is 10, so my degrees of freedom would be 10 minus 1, 9. So this is what my degrees of freedom. So using a t distribution table with the 9 degrees of freedom, you would find that the p-value is 0.043. Okay, so that's what is, you can see that here. So 9, and these are specifically one tail and two tail, and you would find that it's the values around 0.043. So this means that there is a 4.3 percentage here, somewhere around here. So there is a, it's this one, I'm talking about this value 4.2969. That's now about the 4.3 approximate, the 4.3. I'm checking the approximate value. Okay, so this means that there is a 4.3 percentage chance of observing a t value as extreme or more extreme than 2.31. So assuming the null hypothesis is true. So you can take the more example from here. So in summary, to calculate t distribution, you need to know the degrees of freedom and the value of the t statistic. The degree of freedom represents the number of independent observations in the sample and are calculated as the sample size minus 1. The t statistic is calculated using the sample mean, so sample standard deviation, hypothesized population mean, and the sample size. Once you have the t statistic, you can use a t distribution table or a software to find the p value associated with that t value and degrees of freedom. So here let us take 9 and 2, I'll go with the 2.31 and execute. So this portion I got somewhere, this is the portion. So the probability is this one. So from here to here, 0.97 from here to here, and only outliers, it's 0.04624, and the central part, it's 0.95 percentage. Okay, but I just want to have this positive outlier, it's 0.02312. That's what my it's 2.31 value. This is what my value. Okay, I just want to show you that value 2.39 t statistic. It's not that here we got the probability value, but I just want to show you that x, if you just give some x value, so what's that value, it will be converted into that 2, and this one, the probability of that x is this much. That's what I'm trying to show you here. Okay, let me give some 2. It's okay, I just want this portion from here, it's 0.03828, and if I give yeah 2 and put it into this one, you see that, so 0.92, so total it's 0.92 percentage is covered up here. Okay, that's what is our student t distribution.